Good morning once again. Now I will talk about more industrial projects. In fact, this is dealing with two projects that we are working on, and I will provide you some lessons learned about these applications in industry. It seems that my this doesn't work. It's on, but maybe perfect. So I will start with like a brief introduction of the production system. If we are talking about Lego, maybe most of us associate the company from Denmark, but relatively few people know that the biggest packing line of Lego over the world is in the Czech Republic, in Kladno, close to Prague, and this packing line that I will talk about is just packing. It's not molding the bricks, but it's calculating the right number of Lego elements, Lego bricks that should be included in the plastic bag. So if you are buying some Lego set for you or for your kids, or then typically there is the paper box, and inside are the plastic boxes with or plastic bags with the bricks. And this presentation I will provide to you right now is about how about packing the Lego elements, Lego bricks into these plastic boxes. So here is the example of one of the production lines, one of the setups that are used for this kind of packings. The line consists of two in fact lines that are called strings, and both strings include so-called counting machines. These devices, here you can see it better, calculate the right number of bricks of the same type, put it into the box, and afterwards the box is packed and prepared for the final packing. The thing is that you can see that all those devices are equipped with their own computers, and on these computers human operators have to set up the right configuration, how these vibrations should be set up, what's the amplitude of the vibration, what's the velocity of the conveyor belt, but also many other parameters, like some ramps, when the amplitude is changing, how this ramp should what should be the slope of this ramp, and the line is operating in various modes, so what should be the setup in all those modes. Overall, it means that the human operators have to set up more than 30 parameters on all machines, and setting up this manually significantly affects the time needed for changeovers between different productions. So the changeover is some time that is not productive. And it's very important to shorten this non-productive time, and we did it with AI methods, but also to improve the quality of the setup, because every human operator prefers different setup. human operators are of different skills, and it makes sense to have some supervisory system that supervises the production of the entire packing line, and that checks and fine-tunes the setups, that assists in the changeovers, and provides some AI-based or data-driven based setup at the beginning of the production. But also to solve and to detect and solve some unexpected situations, like if some device gets blocked, then it tries to solve the situation, or if the computer or AI is not able to solve this itself, then to call the human operator, but call the operator in time, and not after the entire packing line is stopped, and again, this means the non-productive time. So the effort that I will talk about, that we realized, is that we utilized the legacy counting machine that was in the factory, and we improved this machine to provide some smart feature. Therefore, we call it smart counting machine. We started with simulation modeling of the movements of the bricks. Based on the model, we tried to realize some basic from the current point of view, some initial version of the control algorithm that was not good enough, and therefore we then switched to the data-driven approach that is able to learn from the human operators. To be able to introduce the AI-based control, we had to equip the machine with the communication protocol that is capable to transfer all the parameters that have to be set up there, and that were set up by human operators before. We utilized the OPC UA communication for this, because OPC UA is one of the cornerstones of the Industry 4.0, and also we had to automate the so-called scrapers, which are the parts that in the past were set up by human operators. So we had to automate this with servo drives or stepper motors. Transforming the legacy counting machine that was used for many years meant to slightly modify the software and hardware of the counting machine, but also to accompany this improved hardware and software with AI methods that are running on the line level in the industrial PC. And these algorithms are continuously supervising, checking, and adjusting the operation of individual machines. This is just an example or idea how we equipped or how we improved the manual scrapers with automated scrapers. So as I mentioned, we started with simulation modeling of the line and of all that machines. In fact, the simulation model is kind of a leitmotif or some common intersection point in my presentations today, and we simulated what's going on in the machine, and based on those simulations we wanted to realize some linearized control algorithms. Unfortunately, it was not good enough, as I mentioned. Here is another type of simulation that was the signal-oriented simulation in MATLAB Simulink. This is Technomatics or Siemens plant simulation software, which is like statistics-based software that is simulating here the entire packing line, and with this we are able to simulate some local stacking of the line and of the operation, and we are able to evaluate the overall statistical performance of the line. So when we found out that the classical control approach based on linear control is not suitable enough, we started to build a more robust structure that will enable us the data-driven approach. And as I already introduced, what we had to do as the first step, we had to get rid of the slightly obsolete RS485 communication bus with OPC UA over Ethernet, which enables us to transfer significantly larger amount of data bidirectionally and more reliably also. We equipped the line with the AI supervisor or AI software that is continuously monitoring the operation of the counting machines, but also this AI supervisor is grabbing the data, acquiring all data changes that are in the line, logging the data and logging the best so far performance, best so far setups of the machines. And those best so far settings are then used to provide a new setup of the counting machine. It's not that straightforward because we have to take into account that the counting machines are in different have the different history leading to some worn out parts, so some smoothness are different, the vibrations can be slightly different, the calibration of the machines can be slightly different. So it means that we have to use the AI methods. We are using, for example, clustering to aggregate the data, and we have to distinguish on which particular machine the data was acquired. So we are like coupling the Lego element and the particular counting machines, and we have to support some kind of generalization, meaning that if some setup works on one machine, therefore there is some chance that it will work on all machines. But on the other hand, we have to take into account that the machines are different, therefore we have to somehow distinguish between the machines. And if on one particular machine the setup was different than in the whole factory, then maybe it's right, because that particular machine is not in a good shape. It's not properly calibrated or something like that, and we still have to consider this fact in the setup of new values for that particular counting machine. So we have introduced several automation levels. The first one is the manual control, which is more or less the state as it is now. Plus, we are logging all the data from the counting machine, but the automatic intervention is off in this level. Then we have the second level, which we called first best experience, and this is kind of support of the changeover of the production, meaning that the clustering algorithm provides the best expected setup for each counting machine, each type of bricks, each number of elements that is calculated on the counting machine. Then we have like the third level, which is called continuous AI control, which is based on continuous monitoring of the machine and trying to slightly fine-tune the setup by slightly modifying some of the values. In fact, the algorithm is based on some kind of hill climbing, but we are trying to we don't want to stuck in some local optima, therefore we are using the simulated annealing algorithm right now, trying to avoid reaching the local optima and not the global optima. And finally, we have the four automation level, continuous experienced AI control, that combines these two levels, 2 and 3, plus it's adding some further features like some trying to call the operators or solve some operation, some situations in the operation if the system itself can solve it, for example, by suddenly changing the setup for some temporal time, trying to get rid of some situation like some stuck element, and then returning back the setup to the previous one and things like that. This is the example of the applications or maybe prototypes of the applications that we've implemented. We have there some remote control, remote monitoring. We can see continuously the parameters. We can select which parameters do we want to see. So this can be considered as something like visualization or some kind of SCADA system. We can remotely set up some values even if we are not close to the machine. We can do that remotely. Plus we have there some kind of dashboarding showing what's the performance of the counting machine, visualizing what's which of the machine on the line is the best one from the performance point of view, which is the worst one, and therefore to which one the human operator, if he or she is there present can look at and improve the setting. So by now I was talking about performance measurement, performance analysis. Now I will go more to the energy measurement and optimizing the energy needs of the production. Right now, the energy efficiency is a big topic, not only in industry, but industrial systems are very sensitive to the changes in the price and availability of cheap energy. Therefore, it makes sense to also continuously monitor not only the performance, but also the energy consumption, and in ideal case to correlate the quality of setups in terms of performance also with the energy consumption, because it can happen that we can find the setup that is performing the same as another setup, but with lower energy consumption. And therefore the AI control should also consider this and prefer the setups with lower energy consumption. So typically in this type of applications, we are starting the project with energy measurement, energy monitoring. Therefore, we've mounted the measuring set into the line, and we are acquiring the data also for all energy loads that are in the line. This is the example of the energy consumption. I had to remove the numbers here on this axis due to confidentiality reasons, but you can see that we can see two counting machines here that have higher energy consumption than the others. We can see also the balance between the strings, which is now relatively the same, or the energy consumption of both strings is the same, but in some cases it's significantly different, and maybe therefore it makes sense to somehow balance this from the practical production point of view. With this kind of data, we are not only wanting to measure or visualize the maxima and to pinpoint the operators to those machines, but also to go towards some kind of energy labels for the production, because the production of different goods, different products can have significantly different energy label, and most of us knows the energy labels that are on the white goods or electronics that we buy in the market, like for household. But in the industry, it's very rare to have this kind of energy label for each product. And therefore we are going towards this kind of energy labeling to get the better insight also on the into the energy needs. That can be afterwards used for the energy optimization. In the last phase of this project, periodization should be the optimal control or the energy aware control that takes into account the energy consumption for each product and tries to modify the setups and the control processes for each from the energy point of view, and not only from the output cycle point of view.